Another quality of solids is a physical property known as specific heat. Specific heat is defined as the amount of heat energy needed to raise the temperature of 1 gram of any substance by 1 Celsius degree. This goes back to our chapter 6 a little bit when we learned about calories and joules. Calories and joules, we said 1 calorie was the same as 4.184 joules. And we defined really the specific heat of water at that time. We said it takes 1 calorie of energy to raise 1 gram of water 1 Celsius degree. Or in the metric system, we defined it as saying it takes 4.184 joules of heat energy to raise 1 gram of water by 1 Celsius degree. I'm telling you the specific heat of water when I'm giving you that information. But every substance has its own unique value of specific heat. Just like density. Density is unique to each and individual compounds or elements. It is an intensive property that gives us a quality related to, if you remember, density is mass over volume. This is a property just like specific heat, unique to each individual compound. And the reason we're bringing it up here is we can study specific heats of metals. So specific heat, the larger the number, the value, the magnitude of the specific heat, it takes more and more and more and more energy to raise the temperature of 1 gram of a substance by 1 Celsius degree. So if I put in a little bit of heat, it doesn't move very much on the temperature scale. So if you compare, say example, 4.184 joules per gram degree Celsius is that specific heat for water. And let's say I have a metal coming in at 0.2 joules per gram degree Celsius. Adding the same amount of heat, the water hardly warms up at all, and the metal will get really hot really fast. Here are some examples of specific heat of substances. In the left column, these are all examples kind of just written out here. We have aluminum, 0.214 calories per gram Celsius. See that calorie unit? Or in the metric system, a joule per gram degree Celsius. Remember the conversion. 1 calorie is 4.184 joules per gram degree Celsius. And you can see that right here. That's the very definition of water, right? That's our base of the system. So we can just see a list of all these different substances, and the term specific heat is applied to them, telling me how many calories of energy or how many joules of energy it would require to warm up 1 gram of that substance by 1 Celsius degree. And if we want to calculate, we can consider calculations in terms of the mass, the specific heat, and the change in temperature. Let's do some thinking together. Considering the elements aluminum, copper, and gold. So just a moment ago I had this screen up, aluminum, copper, and gold. I think this is in your notepad for your convenience, but just so I didn't have to go back and forth on the slide, I wrote them down here. Aluminum, copper, gold, and here's iron, just from the table on the previous slide. Aluminum has a value of 0.214, copper 0.09, gold 0.03, and iron 0.107. Those are in calories per gram Celsius. What if you put in 10 kcals of heat to each of these elements, same amount? What element would have the highest temperature? Which one would warm the most? What do you think? Which one has the lowest specific heat? The one that doesn't take much energy at all to convince it to warm up. Looks like gold. The gold specific heat is 0.0310 calories per gram degree Celsius. So thinking about How much would it raise if I added 10 kcals? A lot. And which one would hardly move at all? Which one is the biggest specific heat number? Aluminum would be this 0.214. And again, just comparing, this is the smallest specific heat value. This is the largest specific heat value, meaning that this element, gold, would change temperature the most. Which element would require the largest amount of heat to raise it by 5 Celsius degree? And that's going to be the largest one, right? It's going to take a whole lot of energy to get aluminum because it has the highest specific heat value. The higher the specific heat, the more energy it takes to raise it by 1 Celsius degree. The larger the specific heat, the less the temperature of a substance will change when it absorbs energy. The larger the specific heat, the more heat that must be added to increase the temperature of the substance. And that's what we just wrote on that previous slide. Well, let's introduce a formula to how to calculate specific heat. We can calculate heat released or heat absorbed. Heat absorbed we know to be endothermic. Heat released is to be exothermic. Heat is measured in calories or it's measured in joules. The heat unit is a calorie. We can calculate that by taking the mass times specific heat times the change in temperature. Heat gets a letter Q for a symbol. I don't know why, but Q is given to heat. M stands for the mass measured in grams. Delta T stands for the change in temperature. And just think about what that means. You would find a change in temperature by knowing its initial and final. So T final minus T initial is how much it changed by using a thermometer. And then you're going to get the specific heat, and it's given a little letter C. The specific heat is the other variable in this equation. And that's the unit then, this could be in Celsius degrees or in Kelvin, because when you subtract, you're going to get the same difference. If I subtract two numbers on the Celsius scale, I would get the exact same answer if I had subtracted those values on the Kelvin scale. So it doesn't matter if we're in Kelvin or Celsius here. If my heat is measured in a calorie, my unit for specific heat is calorie per gram degree Celsius. If it's measured in a joule, it's joule per gram degree Celsius. So we're just matching units. Q is equal to mc delta T. That is our formula for calculating heat. I have this nice little tool that helps me remember. Draw this with me and it will help you with the algebra. Here's Q on the top, and I can find Q by multiplying m times c times delta T. And this allows me to use this little visual where I can cover up the variable that I want to solve for and see the relationship to the other. So cover up Q, just cover this up and you get m times c times delta T. If I want to solve for specific heat, cover this one up and you get Q over m times delta T. So it's just a little, a little tool, a little visual to help us remember the algebra. Q on the top is found by taking mass times specific heat times the change in temperature. Shall we try one? How many calories are needed to heat a pot of water from 25 degrees Celsius to 100 degrees Celsius. I'm going to make that bigger. Q is equal to M times C times delta T. We're being asked for calories, so this is what I want to know. That's the one I'm going to cover up. I have 1,600 grams of water, and my temperature change will be the difference from, here's your initial, here's your final. So delta T is 100 minus 25, which is 75 degrees Celsius. We'd like to know Q. Well, you know what's not given on this page, but we're expected to know it? What is the specific heat for water? Now, I know that I gave you a table, but this is one that you should really just know. Know this one. 4.184 is equivalent to saying 1 calorie. So it's 1 calorie per gram degree Celsius. That's what I have to know right here. 1.0 calorie per gram degree Celsius. So I want to know Q. I'm going to find that by multiplying M times C times delta T. 1,600 grams times 1 calorie per gram degree Celsius times our delta T, which was 75. Notice how grams canceled? Do you notice how Celsius canceled? And when we multiply M times C times delta T, you found Q. And Q comes out to be calories of energy. So we're just going to take 1,600 times 75 degrees Celsius, and we get a big number. How many zeros is on your screen? 120,000? And there's your answer. 2 sig figs? That will work. How'd you do? Shall we try another? How much energy is required to heat 28 grams of iron from 19 degrees to 150 degrees? Report your answer in calories and in joules. My formula, my little helper, Q is equal to M times C times delta T. What do we know? Well, we were given 28 grams. I can place that here. That's the mass in grams. The temperature change, initial was 19, T final was 150. So the delta T was 131 Celsius degrees. We want to know energy, and that's Q. How much energy? That's heat energy. And the C, the specific heat constant. Well, again, I gave you this chart. You do not have to memorize all of these elements. Don't think that for a minute. But I do expect you to remember water because it is the basis of that whole metric system. But what I did was just kind of clip art for us iron, since it was the, I just pulled that from the chart. Now in a calorie, we'll use 0.107, and in a joule, in a second calculation, we'll have to use 0.448. So heat measured in calories, we'll use 28 grams times 0.107 calories per gram degree Celsius times our change in temperature of 131 degrees Celsius. Grams canceled, Celsius canceled, and we arrived at calories. 28 times 0.107 times 131. My screen reads 392.476. And let's just make sure we give that, looks like 2 sig figs. Shall we write 390 calories? What about in joules? Q measured in joules would still have 28 grams, same mass, Same temperature change, but what will be different is the specific heat. We have to make sure we grab that in a joule per gram degree Celsius, but the same temperature change. See what we've done? Grams canceled and Celsius cancels, and we're going to end with joules of energy. Let's hit that. We have 28 times 0.448 times 131. My screen reads 1643.26, but let's do that to 2 sig figs. 1600 joules. M times C times delta T are units to help us find heat energy. How about another? How much energy is released by 200 grams of water? So when we're asked to solve for energy, that's our Q. And we know that it's found by taking M times C times delta T. We're given 200 grams of water, and it's cooling from 55 to 12 degrees. So here's your initial. Here is your final. Now, final minus initial. This is going to give us a negative answer, but that's okay because it's heat releasing, exothermic. Heat releasing means we'll have a negative value for exothermic. So right here, this is negative 43 degrees Celsius. Specific heat of water in a calorie we know is 1. So we'll take 200 grams of water times its specific heat of 1 calorie per gram degree Celsius. And just in your head, remember, it takes 1 calorie of energy to raise 1 gram of water by 1 Celsius degrees. And we're letting it cool by 43 degrees Celsius. When I calculate, I get negative 8,600 calories. And the negative just simply means exothermic, heat releasing. Now I can convert that into a kilocalorie. Whoopsie. 1 kilocalorie is 1,000 calories. And so I'll just slide the decimal 3 spots to the left to convert my calorie into a kcal. And there's that answer. Not too bad, not too bad. Here's an example of using a different compound called 2-propanol. And all I did was go to your chart and I pulled off its specific heat. So now, remember, our little helpful hint here, Q is equal to M times C times delta T. And let's just fill these in as we read it. It says 400 calories of heat. That's this variable. We're given Q this time. Of 25 grams, that's a mass unit, of propanol at 21 degrees. Well, this is the initial temperature. We're being asked to solve for the final temperature. So this is what we want to know. I need to figure out how much it changes by so that then I can figure out where it will land. So 2-propanol in calories. That's this number right here. So this time we know Q is 400 calories. I want to know the specific heat. So I have 25 grams times 0.612 calorie per gram Celsius. And that's going to give me my delta T. So this is what we want. You see what we have? Q over M times C. Q over M times C. And that's going to pull out delta T. So hit that with me, your key sequence, 400 divided by parenthesis 25 times 0.612, close parenthesis. Now my screen reads 26.144. Well, just right there is fine. Now that's not my final answer. That's my delta T, how much it changed by. If we're adding heat means it's going to warm up. And think about that. If the initial temperature started at 21 degrees and it warms up by 26 degrees, I'm going to keep the 2 sig figs we need anyway, right? Added to means it's going to warm up to the final temperature, right? This will be a bigger number because I'm warming it. So it's going to land at 47 degrees Celsius. It changed by 26 degrees Celsius, so it would end at 47. We're taking the initial and adding the change to find the final. Think about what I just said there. TF minus TI is delta T. So if you just think about what we said, you're going to just rearrange that and say to find the final, it's delta T plus the initial. And that's how we found 47 degrees Celsius. Pause and think this through. Give yourself a little think time and try this problem out. Come back to me when ready. We have 2 separate problems here, don't we? We have to solve for copper and then for mercury. I know that Q is equal to M times C times delta T. We want to know the final temperature, so we better solve for delta T. That's what we want to know. Now, both of these are giving me 20 calories of heat, and they're both giving me 10 grams, but I've got to solve 2 separate problems, one using the copper and one using mercury. So let's set up for copper first. With copper's value of 0.09, this looks like my math. Delta T will be solved for by taking our 20 calories and placing it over our 10 grams times the specific heat of 0.09 calorie per gram Celsius. This is your Q, this is your M times C, and you're solving for delta T, right? This is the one you want, so you cover it up and you see the algebra, Q over M times C. So let me hit that for us. We'll have 20 divided by parenthesis 10 times 0.09, and I hit and it says 22.22 degrees Celsius. Now if it started at 15 degrees Celsius and you added heat, the new temperature will be 22.22 degrees higher than 15. So I'm going to just add those two together, and the final thermometer will be 37.22. I'll just leave, that's close enough, 37 degrees Celsius for copper. What about for mercury? Its delta T would use the same 20 calories, the 10 grams that you had, but now remember mercury has a different specific heat, so 0.0335 calorie per gram degree Celsius. Remember that in a parenthesis down there. Remember, we want to solve for temperature, so you see your formula, Q over M times C. 20 calories divided by, parenthesis, 10 times 0.0335. And this time the delta T came out to 59.7 degrees. If the initial temperature was 15 degrees, the final temperature is simply adding those together. So while I have 59.7 on my screen, I'll just add 15, and this would end at 74.7 degrees Celsius. So clearly the mercury warmed up significantly compared to the copper.